So we are going to lesson 4. Part 1 is doing this beautiful video from Party Sabetti. Why didn't it go? Oh, it didn't go. I gotta find it. We'll get it this way. Against all odds. Party Sabetti, give me a fitting line to data. Here we are. We're gonna talk about snow. This one is actually kind of cool because it is all about water sources that are drinking water sources, right? We're very lucky. We actually have a lake here, correct? And that water, besides rainwater, and that can be cleaned up, right? We do get snowfall water as well, but this is about the West Coast, which had terrible fires in Los Angeles this past January, right? Lots of fire damage. All right, here we go. Let's Party Sabetti it up. Where are you, girlfriend?
Hi, I'm Party Sabetti, and this is Against All Odds, where we make statistics count. Scatter plots are a great way to visualize the relationship between two variables, such as ocean temperatures and coral reef growth. As temps go up, new growth goes down. Or between femur bone length and overall height, as seen in this clip from Bones, Fox's show about a forensics team.
A lot of jewelry, male. Thigh bone suggests he was tall. ID bracelet.
Forensic anthropologists know from years of collecting data that there's a relationship between the length of your thigh bone and your total height.
That makes a difference?
Facts of life, Bones.
In this case, the femur length is what influences the total height. Remember that the explanatory variable, femur bone length, goes on the x-axis, and the response variable, total height, goes on the y-axis. The data points appear to fall pretty much along a straight line. Longer thigh bones and taller heights look like they go together in a linear relationship. Statisticians call the line that describes how the response variable changes with the explanatory variable a regression line. Any straight line can be described by the equation y equals a plus bx. A is the y-intercept, the spot where the line hits the y-axis, where x equals 0. B is the slope of the line, how much y changes when x goes up by 1. X and y are the data points you're plotting, in this case, the bone and height measurements. Sizing up the data points, we can just eyeball where the line should fall. But there's a statistical technique to figure out how best to fit a line to the data. Once we have that line, we can use it to make predictions. That's how Brennan on Bones can estimate an unidentified crime victim's height even when she has an incomplete or damaged skeleton, just using the thigh bone measurement.
Approximately 6'7", right-handed.
6'7".
This man was dead for several hours before the train hit him.
The Colorado Climate Center uses regression lines in a less sinister scenario to forecast the state's seasonal water supply. Farmers, city planners, businesses, it's important to all of them to know how much water is going to be available each year, so they can plan accordingly.
The sooner you know that, the better you can strategize for planting crops, for managing landscapes, golf courses, for knowing what water can be stored in reservoirs, for understanding what water will be available to meet the interstate compacts on the various rivers. The big question is, how can we predict the water supply we're going to have as far ahead of time as possible?
Most of Colorado's water comes from melting mountain snows in the spring. So climatologists have developed a model based on two types of data: the amount of winter snowpack in the high elevations and the resulting volume of water that flows out of the mountains throughout the summer.
And what you really like is to have many years of that in the past so that you can see how the snow water content in the mountains over time has related to the amount of water flowing down the river during the late spring and summer.
So Colorado's Natural Resources Conservation Service heads into the Rockies to collect that data.
They've got hundreds of sites in the Colorado mountains, and they monitor those on a monthly basis. They do that by identifying sites that they return to year after year after year. And they collect a minimum of 10 depth and quantity subsections on the snowpack, and then they average those to come up with the total for that particular area.
So that's one part of the model, the water that's stored as snow all winter long. The second set of data that climatologists need is how much water actually ends up running downstream.
The U.S. Geological Survey operates a network of about 300 gauging stations in Colorado. At each one of those locations, we have a recording device that continuously logs the height of the river, and then we come up with a continuous record of discharge at each one of these 300 sites.
Let's graph these data points on a scatter plot. You can see that in the years when our explanatory variable, the snowpack, was high, the spring runoff, our response variable, was too. It looks like a pretty strong, positive, linear relationship. Of course, in the real world, all data points don't fall on an exact, precise line. So we need a technique to figure out the regression line that minimizes the vertical distances of our data points from the line. Let's zoom in on just these 3 points from our Colorado water data. We want to find the best fitting line with the most points as close as possible to it. This vertical distance of a point from a line is called a residual. As we shift the line, some residuals get smaller while others get larger. They can't all be small at the same time, so we need to find that sweet spot where we've gotten them as a group as small as we can. Statisticians use a method called least squares to do that. Since some of the residuals are positive, above the line, and some are negative, below the line, we square them, which makes them all positive. If you add up the squared residuals, the bigger the sum, the more the line misses the points. So we want to make that sum as small as possible. Software can do the math for you and come up with the equation y hat equals a plus bx to describe our line. We say y hat to emphasize that we're talking about the predicted value of y, not a measured value from our data set. Now we have our regression line and can use it to make predictions. Remember, the plotted points are our actual data, and the regression line predicts the y value for any x. Back to the Colorado water data. Statistical software gives us the equation for the regression line. The slope of 1941 predicts that for every 1-inch increase in snowpack, the runoff increases by 1,941 acre-feet. The y-intercept is negative 7,920, which would seem to say that if the snowpack was 0, the runoff would be around negative 8,000 acre-feet. Obviously, that doesn't make sense, and it's a good reminder that you can't extrapolate from the regression line too far outside the range of the observed data. Keeping that limitation in mind, though, the regression line can be very useful for Colorado water users.
We have found that it really does predict the amount of stream flow that we're going to have months in advance.
If you know that this winter, the Rockies saw 30 inches of snowpack, you can look at the line to predict how much water is going to flow into the system in the spring. Here's the spot on the line, and plugging in the numbers to the line's equation gives us a forecast of 50,310 acre-feet of meltwater. That's a number that can help water resource managers plan for the year ahead. The regression line works well to predict the Colorado water supply because the relationship between snowpack and river flow is linear. If the relationship you're trying to describe actually has a curve pattern, a straight regression line won't be a good fit to the data. For instance, check out this scatter plot showing the curve relationship between an alligator's length and weight. Trying to use a regression line in a case like this won't make the most accurate predictions. One way to assess how well a regression line fits the data is to make a residual plot. That's a scatter plot of all the residuals against the explanatory variable. It's as if you turn the regression line horizontal. If the dots in the residual plot appear randomly scattered with no strong pattern, like they do in the Colorado water case, both above and below the line, then the regression line has nicely captured the pattern in the data, and a linear model is a good choice to describe it. But if the residual plot looks at all curved, like in the case of our alligators, then the data pattern is curved and the linear model is the wrong one to use. Probably best to steer clear of those alligators, especially if they're hungry. You wouldn't want to become a meal that would add to their weight, no matter what the relationship to their length. For Against All Odds, I'm Pardeep Sabeti. See you next time.
So the relevancy of that is actually super important. I want to just see if I can find it real quick. The Colorado River, water, feeds lots of different states on the West Coast. So 19 hours ago, I guess that would be pretty relevant. So, and then there's this information about the rights of who has rights to that water flow. Okay, so here's let's see, historic Colorado River deal to conserve flow. What? No, I don't want to log in. I just want to read. Will you let me read? Oh, jerk face. I hate it when. Oh, here we go. Advances after winning key approval from the State Water Board. So there's this whole process of who gets how much water from the Rockies. And there are different rivers and different parts of the mountain ranges that feed different parts of different states. But the Colorado River is one of the most important ones for our West Coast. So if I go back just one more, these are all like a week ago. Ooh, states that rely on the Colorado River miss deadline to agree on cuts. 7 states that rely on the Colorado for drinking water. So what's at stake for California? I mean, we don't live on the West Coast, but we're very lucky to be by a Great Lake. Okay? So just to know that this is relevant data and conversation. All right, so we are now going to go to our notes and look a little bit more as to how you get this linear regression equation and what those least squares are. We're going to actually be able to make squares in our calculator. I kind of like this activity. So it should be, that's the whole point of today. All right, if our data shows a linear association between the explanatory and the response variables, we will find the line that best fits the correlation. All right, so the line is called a regression line. And then the equation is y hat, so that's how you say it, y hat equals a plus bx. All right, so why do we have y hat? Y hat is because it's not actually the y data points, it's a predictive model. Okay. All right, so once again, specifically it's called, a least squares regression line, which makes the vertical distance from the data points to the regression line as small as possible. So it's called least squares because we're actually finding the smallest area of those squares, like the sum of all the squares, what's that's going to be. So here is kind of an example of what's going on. So the line was drawn, here were your original data points, right? 1, 2, 3, 4, 5, 6. If we only look at the vertical distances, we have 4 down and 2 up. That would be the residual. And that's kind of what we were doing when we were playing, just with our ruler, making it happen. But when I take this same distance here and go, and make a square out of it, right? I can then find the area of this square and the area of all the squares, and I'm going to add up or find the sum, the areas of the squares. And what's going to happen then is as you move the line around, the total area is going to change. And basically, you're kind of, if we were to plot all those areas on a graph, it's kind of like those areas are all here. You're looking for the minimum area, right? This is our least area or least squares. And that's when the line is in its best position. And your calculator, when it makes the equation, is doing all that for you. Like, it's kind of crazy. It does all that for you. Bless you. All right, so here we go. We're just going to do one by hand, and then we're going to have our calculator do the other. So I want you guys to draw. You take your straight edge. Everybody got a straight edge? Do you need a straight edge? Anybody else need a ruler? Draw a line where you think it should go. Do you need a straight edge, Yancy? Okay. On that graph, where do you think the line should go? Okay. Oops, that's not a line. I don't want blue, I want red or something red. Okay. All right. Do you think everybody in the room drew the same exact line? No, definitely not. Are we all approximately the same? Sure. Okay, so let's just then talk about what a residual is. So pick a point that's above your line, okay? So I'm going to pick this one because it's closest to me, and or like it's pretty far above, and you guys can see what I'm going to do. Okay, so this is kind of where it's hard because you're so distracted by the line you just drew. Try to drop the line straight down. I'm going to use a green marker here. Straight down, like vertically, right? Do you know what I mean? Vertically drop down. This green line is called a residual. And I can do the same thing on a point that's below the line. I can, vertically go up to this point, that's a residual. But the problem is if I have positives and negatives, they cancel each other out, right? So that's why we're squaring. So you can draw your square in either direction. And this is why doing it by hand is hard. Because it's like, not like you're measuring this, but like I'm going to try to draw it this way. Okay, I think that's not bad. I made a square, right? But then if I actually do it with my technology, even just this, I can probably get a better version of like, kind of like that, right? See how I made a square out of it? So what the computer is doing, what your calculator is doing that for all the things. Now, your squares are going to be different than my squares, right? It doesn't matter if you do the square to this side or to that side, okay? It's just what is the area of that square. We add them all up, and whoever had the, guess what? Whoever has the smallest area wins. That's why it's the least area, okay? All right, so now let's go ahead and actually do this with our calculator technology. This is kind of the cool part. And we only play with the squares once, and then we just let our calculator always do the work for us. Make sense? Okay. So when you turn the page, you guys can see there's a data table. So the first thing we're going to do, and we want to make sure we all have the same data table so life goes well here. So when you turn the page, you want to title your two columns. Let's make this one, you could just put temp. And then for the other one, just put like I think if you put ICS, it's like ice cream sales. That would work. All right. So this is going to be your classwork grade for today, participating in this calculator skill. Okay. Because this is kind of like doing a lab. Ooh, Miss Rob, you're so savvy. Okay. So in our lists, I'm sorry, Maddie, I keep driving in front of you. If you want to sit in a different seat, you're totally welcome to. I don't mean to drive in front of you. It's just a reflex. So I'm going to go up here and I'm going to title this temp. So you have to title your two columns. Oh, it won't let me do capital letters. Oh, well. And then you're going to type in your data. You ready? You ready? You know when you're ready, Mandy, okay? All right, so all the things are off to the side. It says create a scatter plot. All right, so do you remember how to do that part? So if you don't remember, good. Okay, so you're going to add a page. So you go Control, Doc, and you want a 5-page, right? And if you titled your data, you should see points. So we want to put temperature on the bottom. And our temperature is in Celsius. And then we're going to put over here on the side, ice cream sales. Okay. Now just look at somebody's next to yours or look at mine. Do we all have the same thing? Or does anybody have do I have a bad data point? What's this data point? 27. There is no 27, is there? Okay, I have a bad data point. Let me go back. 408. That's supposed to be 17.2. Pardon, let me fix that. Okay. Does everybody kind of look like this? Okay, good. Sorry about that. Okay, so now, this is a one-time activity. It's kind of cool, though. So now we're going to go Menu, Analyze, Add a Movable Line. Okay? And then it's going to take us a minute to adjust to that. So, Analyze, Add a Movable Line, which is choice 2. So now this is where you kind of have to play around with your cursor. So if you have your cursor more towards the center, the line moves up and down. You see that how the slope stays the same? If you go to the ends, then you can change the slope of the line. Okay? Does that make sense? Is that working for you guys with the cursor? Okay, just making sure. Okay, so now, now we got to go and show those residuals. Are you ready? So we go back to Menu, and we go back to Analyze, and down at 7, it says Show Residuals, and we want to show residual squares. Okay? All right. So how are we doing? Does everybody have an equation on their screen as well as a sum of the squares? No? Okay, so Menu, 4, 7, 1. There you go. So what you can, yes.
I don't understand what's the point is.
Because we're not done yet.
Oh.
Okay, ready? Your goal is, so I have 14,781. Do you guys have a sum of 14,781? Does anybody have less than that? So what you do is you're moving your line to find the smallest possible thing. Like, I don't know if that's, so like as you move the line around, both steepness and up and down, is there a best place to put it? Now, the fact that I had 14,000 was kind of a dud. Like I should have been way off. But like, do you see how like I'm trying to get the smallest sum? Like that's obviously wrong, right? I have huge things. So your goal is to get down to at least a low 15,000. If you can get to a 14,000, that's pretty good. I have that guy way below though. What happens if I go like, ooh. Like how low can you go? How low can you go? How low can you go? I got down to 14,569. Did anybody get down less than that? No? Did you get at least into the 14,000s or low 15,000s? Okay. So what's the point of this is thank God we don't have to do this by hand. You guys realize that technology keeps moving forward, right? So when we go back to my dad or your parents or grandparents, any of those people that were like the beginning of the IBM computer kind of days, right? A lot of this stuff was done by hand, or maybe at once, at some point some nerd said, how do I get the best line? How do I know I have the best line? Don't you guys agree? Like that eventually is happening somewhere, somebody said. So then somebody's like, I know how to make this the best line. I'm going to look at the residuals. And then somebody's like, yeah, but you have some positive, some negative. How are you going to figure that out? Oh, I'm going to look at the squares of the residuals because that takes that away. So this is all just it's kind of like we're discovering the pure science of where math came from. Okay? So the deal is this. Let's take a moment and write down some information. So you can use mine or you can use yours. I don't care which. Does that make sense to everybody? So I need to write this down on a piece of paper before I move too far forward because I won't be able to look back at both screens. So sum of my squares is, I'm going to say 14,569. So that's my sum. My A is equal to 29.8. I'll just go up. And then my B, oh no, wait, hold on. That's my slope. So my slope is 29 point, that's my slope. I'm just going to write that down. Because just see how like the X is with that first one, it's doing MX plus B. And then my other thing, my y-intercept is negative 154.4. Okay. I'm going to minimize and get out of here. So the equation so first of all, the sum, I'm just going to write this down. My sum was 1,569. Okay, so then the equation that I got by doing it by hand, and I do, so negative 154.4 plus 29.8 X. Okay. All right, so now, of course, is there a better way to do this? Heck yeah, people! We just run the linear regression like we did yesterday to get the correlation coefficient. Do you agree? Okay, so back on your calculator, you're going to just go back to your table. I'm going to put my cursor in the second column just to make my life easier. And I am going to go menu 414, right? Just what we did yesterday. 4 for stats, 1 for stat calculations, 4 for A plus BX. And then our first column is temperature. Our response variable is ice cream sales. And I'm going to scroll to the bottom to make sure I'm not overwriting anything. I look good. I'm going to say okay. And I'm going to get the following pieces of information from my calculator. Does anybody need me to repeat that step? Menu 414. Okay. Yep. All right. So A is negative 159.47. B was, do I have the wrong, do you guys have the same thing as me or do I have a mistake? Is it 150, did you guys get negative 159? Okay, good. 30.1 we'll say, 30.1. Okay, so our regression equation is in the form of y hat equals A plus BX. Why do we use the y hat? Because it's a predictive model. Okay, so y hat equals negative 159.47 plus 30.1x. Okay, so now what does this mean? So x is temperature, right? So as temperature increases by 1, sales, ice cream sales increase by $30.10. So we can write that down. Okay. And then we also could say that sales equals that times the temperature. So you could do it that way. I didn't write, I think I did something different. Sales equals negative 159.47 plus 30.1 times the temperature in Celsius. So now we can use our thing as a prediction. So if this, like, say you're the person that runs a little ice cream stand up by the beach. Is it worthwhile for me to go to the beach if it's 22 degrees out? Am I going to make enough money? So you plug it in. So what is our sales when the temp, our X, is 22 degrees? So once again, this is a great opportunity to use the scratch pad in our calculator, right? Because all we have to do is calculate this. So we go to our scratch pad and we type in negative 159. Oh, sorry, it's mad at me. Okay, and so how much money would we predict to make? $502.73, right? Or $503. Now, why is this helpful? Well, maybe, what did I say, 70 some odd cents? Or whatever. So why is this helpful? One, so think about food trucks, okay? Food trucks are mobile. Well, and if they don't have enough stuff, they sell out, right? They also don't want to overproduce because then they might have waste, right? So it's that really easy balance you got to try to figure out to make sure that you are prepared for what's happening in your business, especially small businesses. Small businesses are hard. All right, that's all I have for today. Isn't that exciting? You're going to show me your calculator to get your points. Show me your graph. Show me your graph. Where's your graph? Let's hear these squares, girl.